Hello everyone, welcome to EE370A, which is a course on digital electronics, and I'm your instructor Dr. Shubham Sahai, an assistant professor in the Department of Electrical Engineering at IIT Kanpur. I'm teaching this course for the first time, so I guess it would be a learning experience for me. And you're also taking this course for the first time, so let us make it a memorable experience for both of us. Before I get into the intricate details of digital electronics, let me give you some disclaimers. So the first disclaimer is that the contents of the slides and the videos are meant only for the students registered for EE370A. Do not share these slides or videos to your friends outside of IIT Kanpur. I have made all possible attempts to acknowledge the source of any materials which have been used to prepare these lectures and slides. And the purpose of reproducing them is purely academic. It's just to make you understand what exactly they mean. However, from my end, no copyright violation is intended. And in case, after taking all these precautions, if there is any inadvertent copyright violation, please bring it to my kind notice and I'll definitely rectify it. And as I said earlier, these slides and videos are not meant to be shared or posted in public spaces, specifically not on any website. And the students having access to these slides and video lectures, that is you guys, have to ensure this. Now the do's for this course: ask questions without thinking about your peers. So what I think about questions is, these questions can never be stupid. What can be stupid is the answer to that question. And that has to come from my side, right? So you don't have to worry about, what your peers will think or something. Ask questions without any hesitation. Also get to know your classmates. It will not only be helpful in discussing course contents and assignments, but sometimes the peers explain you in a language which is more understandable. I mean, there's a gap between the instructor and you, but when you talk to your peers, when you try to understand anything from your peers, it becomes easier. That is my personal experience. And also, if you know your classmates, it would also facilitate, forming groups or copying in the exams if you intend to do so. You are requested to join the weekly meeting discussion links 5 minutes before the scheduled time, that is at 10:55 a.m. every Friday. In case of any problem, not only in terms of academics, if you want any career suggestion or if you want to discuss something else also about your personal life also, please do not hesitate to mail, message or WhatsApp me. It's our duty to not only teach you, but also to mentor you guys. So if you face any problems, please come to us. Genuine problems would always be considered and we'll make all the attempts to resolve them. And we are here for you. And this is my WhatsApp number. You can call me or you can WhatsApp me, ping me there anytime you want. Now the don'ts of this course: first and foremost, do not share these lectures or slides with your friends outside of IIT Kanpur. I have a very strict policy against plagiarism. So it's not a big deal. I mean, almost everyone, even I refer to research papers or books for these lectures or even for my assignments or anything like that. However, we should be very careful that if we are copying directly any sentence or any quotation from any of the research papers or books, we must reference the source and give the authors appropriate credit. In other words, academic honesty, it's really important. I also have a strict policy against copying assignments. So if I find, or if the TAs find out that you have copied your assignments from your friends, you would be awarded 0 in that assignment immediately. I am planning to design the assignment so that you learn something new. However, you are free to discuss with your peers regarding the topics covered in the assignment, but make sure when you write it down, you express it on your own words. And again, I have a very strict policy against copying in the exams. So if I find out that you have copied answer from somewhere or from some of your friend, then you would be awarded 0 marks immediately without any question. And the guidelines also say that we have to report such instances to SSAC. And the penalty, you already know, can be very harsh, including suspension. So I request everyone, please do not cheat. Okay, so with that, let me go to the grading policy. I guess you guys must be waiting for it very impatiently. So this is how I have kind of divided the mode of evaluations and their weightages. And I'll just like to bring it to your kind notice that these mode of evaluations, they may vary depending upon the extent of use of unfair means in the homeworks or mini quiz. So I have dedicated assignments, 15% of weightage has been given to assignments. At before every quiz, what I'm saying. Now let us have a look at the grading policy, which you must be waiting impatiently. So these are the different modes of evaluation and the weightage or marks allotted for each mode of evaluation. So for homeworks or assignments, I have allotted like 50% weightage. For mini quiz, which would be held immediately before the tutorial sessions, there would be 20% weightage. So make sure that you attend the tutorials as well as this mini quiz well. Mid-semester examination would be contributing to 30% of your overall weightage of the course. And end semester exam would be held for 35 marks, which kind of covers 35% of your course. And at this point of time, I also want to give you a disclaimer that these modes of evaluation are as of now. So they may vary. If I see that many students are using unfair means during the homework assignments or the mini quizzes. So these are only tentative. As of now, they are fixed, but as and when, depending upon the extent of use of unfair means by you guys, I can also modify this. So now let us come back to the fundamentals of this course, which is what exactly is analog and what exactly is digital. I mean, why are we exactly understanding or why are we even learning about them? So analog is any signal which has a continuous amplitude. So what do I mean by that? So if let's say the voltage at a node with respect to the ground, so voltages are always with respect to a reference potential. So let us say that the reference potential is ground here. If it's between VA and VB, so there are infinite values of voltages which are possible between VA and VB, right? So this is kind of a continuous amplitude signal. The voltage can take any possible value between VA and VB. Now, what exactly are digital signals? So they are discrete amplitude signals. Okay, so how can we obtain these discrete amplitude signals? So they are simply obtained via sampling of analog signals at particular instances of time or by quantization of analog signals. So how can that be performed? Or let us just go ahead and see how we can obtain discrete levels out of the previous example. So if we enforce that only discrete values of current and voltage in a range is allowed, so that only some possible values of voltages between VA and VB are allowed, then we are making sure that we are kind of discretizing this entire range, which was continuous earlier, and now our voltage can take only these discrete values. In other words, my voltage has now become digital. Now, what exactly is digital? What does it mean? So digit means basically fingers. So since human beings have 10 fingers, earlier computations or even the child, when he learns to compute, he uses these 10 fingers to count everything, right? Even for addition, subtractions, basic arithmetic operations, he uses these 10 fingers. So earlier, the mode of computation used to be this base 10. Why base 10? Just because we have 10 fingers and it is very convenient for us to perform arithmetic functions using them. And these 10 numbers can be represented with 10 symbols going from 0 to 9. However, later it was found that it is possible to do computations even with 2 symbols or 2 digits that are 0 and 1, which forms the basis for your Boolean algebra. And this was kind of formulated. This whole theory was formulated by George Boole, who was a self-trained mathematician, and he was also a professor of mathematics at Queen's College, Ireland. So he came up with this entire theory of Boolean algebra in 1847. And he showed that it is indeed possible to perform arithmetic functions, arithmetic operations with the help of this Boolean algebra, and with the help of only 2 digits or binary numbers, basically. Now, how did this concept of digital circuits come into picture? So the foundation of digital electronics was basically put by Claude Shannon. I mean, you must have heard about Claude Shannon. He is known as the father of information theory. You'll learn more about him in the courses pertaining to digital digital signal processing and all. However, his MS thesis formed the basis for this entire digital electronics. So you can see even at the level of MS, people can contribute so much to research. So Shannon basically he was at Bell Labs and later he also joined MIT as a faculty. He was a very, I would say, multi-talented person, and his thesis, which was basically which basically dealt with relays and all. So he showed that with the help of relay switches, it is also possible to implement these logic gates, which basically George Boole had shown. So he was the first one to kind of show the implementation of these logic gates with the help of relay switches or switches. So that is how this field came into picture. So as I told, he was the father of information theory and he worked with relay switches. Now, why exactly should we go for digital? just because our PM is saying go for Digital India, or what exactly is the reason why we should go for digital? First and the foremost reason is noise margin. So let us see what we know about that. So in digital or in binary logic, we are interested in only logic 0 or logic 1. So typically when we talk about circuits, logic 0 kind of gets converted to a potential which is ground, and logic 1 gets converted to a potential which is kind of VDD, or the supply voltage, or the maximum available voltage on that chip. So it's like, logic 0 gets converted to a voltage of 0, and logic 1 gets converted to a voltage of VDD, or the supply voltage. So the difference between the two is quite large. And regardless of what we are working with, noise is something that is always present. And what exactly is noise? So noise is any unwanted signal that is present along with the wanted signal. So the noise amplitude typically is pretty small, but here, since our logic levels like logic level 0 and logic level 1, they are separated by large distance in terms of voltage domain. So noise doesn't have much effect on them. However, if it were analog domain, or let's say even we are working with, let's say 10 digits, and the voltages are separated by, let's say 0.1 volts. So then in some cases the noise may be comparable to 0.1 volts, and it may lead to erroneous outputs. So if we are talking about digital circuits, and if you are working with this Boolean algebra, and we are using binary numbers, that is, we are using logic 0 as ground and logic 1 as VDD, then we are making sure that noise has less impact on the operation of our circuit. Then second point is robustness. So these digital circuits are pretty robust against operating conditions such as increase in temperature. So typically what happens, once you turn on your microprocessors or your computers or your laptops, they start to heat up. Because of the power dissipated in these circuits, they start to heat up, and because of that, the temperature rises by the Joule heating. So now, since the temperature has temperature rises during the operation time, the properties of the systems may change. However, the change in the property of a digital system is pretty low as compared to a change of properties of an analog system. So analog systems are pretty sensitive to temperature changes, while digital systems are not that sensitive to temperature changes. So it's robust to your operating conditions, or variations in the operating conditions. Then let us talk about scalability. So these digital circuits are extremely scalable. I mean, you can incessantly scale these digital circuits to pretty miniaturized chips. However, the analog circuit technology is still stuck at 28 nanometer technology node. I mean, you cannot find, or you won't find any circuit implementation, analog circuit implementation, which uses transistors below the 28 nanometer technology node. Now, what exactly is this 28 nanometer technology node? So 28 nanometer technology node simply means that in that technology, the minimum feature size, and that feature size is kind of it can be gate length. Typically, it's not the gate length. It can be the gate length. I mean, it used to be the gate length for larger technologies, but once the dimensions came to this nanometer, once it came below 250 nanometers or something, the concept of gate length was not taken as minimum feature size. It's basically the distance or half pitch distance between two metal lines of interconnects in that technology. This will become clear as we read about DRAMs and all. However, recently what has happened is, these technology nodes have just become names, and it has got no relation with the feature size or the minimum feature size that you can carve on a chip. So if we say that digital is already at 3 nanometer technology node, or it simply means that it has scaled significantly from 28 nanometers to 3 nanometers. So there is a scaling law, and it scales by a factor of 0.7 0.7 times every 18 months. That I'll discuss later. But nowadays this 3 nanometer, it has nothing to do with either dimension of the gate or the distance between two wires on a chip. This 3 nanometer is just a technology. The gate length is still 14 nanometers, and the distance between two wires, it's still 10 nanometers, even at 3 nanometer technology. So it's just a name. And going ahead, 3 days ago itself, you saw that Apple is kind of getting TSMC's 2 nanometer chips for use beyond 2024. And also IBM builds the first 2 nanometer chip during COVID-19 pandemic, while others were busy making dalgona coffee. So this is how, you know, the world is progressing. Soon you will get 2 nanometer chips, but word of caution, there's nothing 2 nanometers there. Neither the gate length, nor the minimum feature size, nor the distance between or half pitch length between two interconnect wires. Now, why digital? Another point is data storage. Since in digital we are working with discrete points, so it's pretty easy to, you know, store them. They represent small chunk of data. However, since the analog data is continuous, ideally there are like infinite number of points between any two analog values. So they kind of represent a huge amount of data, and storing them is also pretty difficult. Also, it is very easy to handle digital data. By handling, what I mean is it is very easy to process digital data. So digital signal processing is way efficient and less energy consuming as compared to analog signal processing. Analog signal processing is too resource intensive. First of all, it requires a huge amount of data storage because, you know, the number of points are huge. And second of all, it's also consuming a huge amount of power. So analog signal processing is always less preferred as compared to digital signal processing. Also, there is this property of fidelity or regeneration, which is pretty important in digital circuits. However, you cannot do away with these analog circuits. I mean, when digital is so good, why do people even go for analog circuits? The thing is, the real world is actually analog. So the world in which you live, everything is continuous in amplitude as well as in time. So the real world is analog. Digital electronics is just a part of that real world. So what happens is, to interface with this analog world, we still need analog circuits. However, these digital electronics, to process those signals, digital electronics is better. And that is why, this world of digital electronics is expanding like hugely. And along with that, since the interface is kind of the analog circuits, so that is also developing. So we cannot, separate these two out. Whenever we will have developments in digital circuits, we are sure to get developments in the analog circuits. Just because, the interface between the real world and the processing world is this analog circuit. Now let us go back to the historical perspective of, computing engines and all. So Charles Babbage, who is known as the father of computer, he found the first difference engine, which was kind of, a mechanical computing device in 1832 itself. Now, this device, it may appear very primitive, but it's very close to, our modern CPUs. It supports, arithmetic operations in any random order, similar to what, our modern CPUs offer. The best part is, they also introduced the concept of pipelining in this kind of difference engine. So what exactly is this pipelining? So pipelining simply means, processing parts of different instructions parallelly. And by doing that, by just processing different parts of those instructions parallelly, we are able to parallelly process different instructions together. So this pipelining will be dealt with in detail in this course. However, that was introduced way back in 1832 itself. So that's a huge achievement, I would say, of Charles Babbage. However, you can see that it's quite complex system and its cost is too high. I mean, in that time, in 1832, you can see that there were 25,000 parts in this machine, and its cost was close to 17,500 pounds. So in 1832, this was a huge money, and because of this, they were not even able to build the entire device. So when was it built? So it was actually built in 1991 itself by a team of Australian engineers, and the device that they built, it is kept in Science Museum in London. However, its size is too large. I mean, since it's a mechanical computing device, its size is too large. So what could be the solution to reduce the size? So the solution came with developments of these electronic devices, and what people suggested was, instead of going for mechanical kind of computing engines, let us make them with electronic devices. So let us see what were the electronic options at that point of time. So, however, the development in the field of electronics was pretty slow at this time, and a huge breakthrough came only in 1904, when the field of electronics was revolutionized with the discovery of diodes. So the first diodes that were discovered were these John Ambrose Fleming's diodes, and then people also came up with these triodes in 1906, which was the Orion triode invented by Lee De Forest. Earlier, vacuum tubes were used for making these electronic devices, and they looked something like this. So they had, a metal electrode, which is typically cathode, which is, encapsulated by a glass tube, and then at the end you have an anode. So these vacuum tubes, they suffered from several problems. So one of the major problem was, their scalability. The size of these devices was pretty huge. So you could scale them till, some, centimeters or something, but beyond that, they were not scalable. Ideally, when you want any electronic device, you would want to, you would want that device to perform several functions at the same time. For instance, your mobile phone, you would want it to, act like a camera. You would want it to, process your information, also, edit your photos and so on. So you want your devices, electronic devices, to perform multiple applications together. So for that, you want to incorporate as many devices on the chip as possible. And for incorporating a large number of devices, their size should be very small. So these devices could not be scaled down. So that was one of the major pitfalls of this vacuum tube-based technology. Other pitfalls were, the reliability was pretty poor. I mean, during the operation, you would not know and this device would just burn off. And also, since these were operating at huge voltages, and on the principle of electrostatic discharge, there was a huge power dissipation as well. But with this technology itself, people came up with the first electronic computer, which was ENIAC, and that was kind of built in 1946. So this is one picture of ENIAC. So let me just brag about its capabilities or its components. So more than 17,000 vacuum tubes were used in this ENIAC. 7,200 crystal diodes were used. 1,500 relay switches were used, 70,000 resistors, 10,000 capacitors were used in this ENIAC. It weighed, around like more than 27 tons, and it occupied an area of 1,800 square feet. So you can just imagine a 2 BHK apartment was full of, these many components, and they were performing just computation. And it would take 150 kilowatts of electricity. You can imagine how much power it was consuming. And this was kind of built by the US Army for calculating, the trajectory of artillery. So that was the main application. It was just computing the trajectory of the artillery. That was the reason why this, electronic computer was built. So now let us go ahead and look at the developments in the field of electronics. So let us first read about the curious case of transistors. So in Bell Labs, which was headed by William Shockley, who was a very arrogant person, they set out to invent electronic switches which could be used to make these logic gates and in turn these electronic devices. So Shockley came up with the theory of transistors in 1935 itself. However, since he was a theoretician, he had to hire someone who could come up, kind of realize these devices practically. So he hired physicists Brattain and Bardy, and they were really intelligent people, and accidentally they kind of fabricated this point contact transistor, which was kind of a germanium like transistor, way back in 1945. But Shockley, since he was a very egoistic person, I would say he was a very arrogant person, so he was not satisfied with this. He wanted to do something and take the credit. So for 2 years he worked on it, and he came up with the theory of bipolar junction transistor. So the first transistors to be fabricated were point contact transistors on germanium, and it was only 2 years later that Shockley came up with this bipolar junction transistor, or BJT, which you must have done in EE 210, and which was the kind of most popular kind of device or form of switches which were used for fabricating logic gates until 1980s. And for this discovery, Shockley is credited and known as the father of transistors. However, I would call this an era of dark electronics. Why do I say so? Because this Australian-Hungarian mathematician, Julius Edgar Lilienfeld, he actually came up with this concept of MOS transistor in 1930 itself. So BJT is kind of, after 1980s, it started to lose popularity, and MOSFETs were the kind of choice for CMOS, for industry. MOSFETs were the choice for the industry, for the semiconductor industry. However, just this guy, he kind of in 1930 itself found out the MOS transistor theory, and despite the credit of father of transistor goes to this person who was kind of very arrogant, Shockley. So in 1930 itself, this guy, he kind of patented this. He filed a US patent, and he named it Method and Apparatus for Controlling Electric Currents. So what he kind of built was, so there were these two metal contacts, and here the dotted thing you see over here, this is a copper sulfide layer, a thin layer of copper sulfide. and there are two contacts to this copper sulfide layer, and then there is this thin wire which is going on top of this copper sulfide semiconductor. So copper sulfide is kind of a semiconductor. So it's like, you have one anode, one cathode, and a third terminal. So what exactly he did was he applied voltages between this cathode and anodes, and by applying voltage on this thin wire, he was able to modulate the electronic properties of this semiconductor film, and with that he was able to control the current that was flowing between anode and cathode. So just by applying some voltage on this third terminal or this wire, he was able to control the current between two other terminals, that is this anode and cathode. So that is how he was able to conceptualize this concept of MOS transistor in 1930 itself. Obviously this is not MOSFET, this is a JFET kind of a structure, junction FET. But after this demonstration, he also came up with this idea of MOSFET. He introduced an oxide layer in between this wire and this semiconductor. So that is also something that he did, and that was very close to this MOS transistor theory. Now, what exactly are these transistors that we have been talking about? So transistors are nothing but all the devices where current between two terminals can be controlled by voltage or current at the third terminal. That can be called a transistor. For instance, here I told that the current between this anode and cathode, it could have been controlled by the voltages being applied to this third terminal. So this is a transistor. So that is something which is the definition of transistor. But how did this word transistor come into picture? So this term was coined as trans resistance or transfer of resistance. By whom? So when BJTs were kind of discovered, or when they came up with this point contact device, Shockley kind of announced that he welcomed the lab mates to put a name to this device. So they named it trans resistance. And how they named it trans resistance, or why they named it trans resistance? Because they basically act like a resistor. So it's a resistor, and it appears as if the voltage is being transferred across the device to control the resulting current. So it appears as if the resistance is being transferred from the input to the output, but originally there's no transfer of resistance. You are just applying voltages or currents on the third terminal, and you're kind of modulating the resistance between two terminals. So that is why its name comes as trans resistance or transistor. They basically act like switches in your electronic circuits or digital circuits, and these transistors or these switches, they combine to form circuits and logic gates and further digital systems. So these are like the primary constituents of all the digital circuits. And the first logic gate was made by using BJT or bipolar junction transistor technology, and it was a discrete gate. What is discrete and what is integrated, I'll discuss in the next slide. So the first discrete bipolar gate was kind of manufactured in 1956 by Harris. And then came this era of integrated circuits. What exactly is this integrated circuit? So it basically is a concept for monolithic integration. What is monolithic integration? So monolithic means single stone integration. So what it means in from a perspective of electronics is that we have to realize all the components, whether they are active components like BJTs, diodes, or MOSFETs, or they are passive components like resistance, inductance, or capacitance, on the same substrate or on the same silicon wafer. So this integrated circuit development was done independently by Jack Kilby of Texas Instruments in 1958 and Robert Noyce of Fairchild Semiconductor in 1957. So these two guys are contributed with the development of this IC, and for this they also got Nobel Prize for Physics in 2000. However, Robert Noyce was, he died till that time, and it is a virtue, or it is kind of a rule of Nobel Prize that only alive people can get it. So Jack Kilby alone got it. However, they both kind of came up with this independently. So once this integrated circuit was developed, so they started using these BJTs, using this concept of integrated circuits to develop some logic families. So this TTL or transistor logic was the first kind of logic gate family to be developed using BJTs. They were discovered in 1962, but they dominated the semiconductor industry till 1980s. So till 1980s, all the digital circuits were fabricated using this TTL logic family itself. Why, one of the reasons why even after conceptualization of transistors or MOSFETs in 1930 itself, they were not, practically realized. The reason was because MOSFET fabrication process is really challenging. The fabrication technology at that time was not very advanced. So what kind of prevented this MOSFET fabrication for a long time was, the tools were not that advanced to produce good quality of interface between silicon and silicon oxide. So what exactly you have in a MOSFET? You have like a substrate, which is typically silicon, then you have an oxide on top of it, and then you have a metal gate or a polysilicon gate. So typically, what happened was there was a huge amount of defect because of this improper, I would say, because the fabrication technologies were not that developed. There were a lot of defects at the interface between silicon and silicon oxide. Because of that, even if they applied a huge amount of voltage on the gate electrode, that is polysilicon, they were not able to control, they were not able to modulate the properties of the semiconductor, or the electric field was not able to penetrate through the semiconductor and do whatever is necessary for transistor action in a MOSFET. That is, field effect was kind of very poor, just because there was a lot of defect between at the silicon and silicon dioxide interface. So that was kind of, gradually the fabrication process improved, and now silicon oxide interface is one of the best interfaces in the world. And in terms of Pauli, who gave the Pauli exclusion principle, he told that interface was created by the devils, while God created the bulk. So interface is something which, I would say inhibited the development of MOSFETs for a long time. But with the advent of fabrication technology, it kind of improved, and now MOSFETs are kind of the dominant technology. So once people were able to overcome the fabrication challenges, they started producing MOSFET-based logic gates as well. The first ones to be fabricated were PMOS devices. I would say the PMOSFETs-based logic, only those were used first. Reason being that, PMOSFETs are kind of more robust to this interface quality as compared to NMOS-based logic. Then they kind of, when the fabrication process further improved, they were able to, manufacture even good quality NMOSFETs, and then they shifted to NMOSFET only logic. Why this NMOSFET based logic is better as compared to PMOSFET logic is, because the mobility of the majority carriers in NMOSFETs is electrons, and the mobility of electrons is kind of higher than the mobility of holes, which are kind of the majority, or I would say the inherent carriers in your PMOSFETs. Since the mobility of electrons is larger than that of holes, therefore NMOSFETs could give you larger currents as compared to PMOSFETs. And larger currents simply mean higher speeds of operation. Because in these circuits, typically you are charging and discharging few capacitors. And charging of capacitor or discharging depends upon the amount of current that is flowing through it. So if the current is large, capacitor charges or discharges pretty quickly. And that is why your NMOS based logics were kind of faster as compared to PMOS based logics, and they were preferred. So encouraged by the success of this NMOSFET only logic, Intel in 1971 came up with its first microprocessor that was purely built using NMOSFETs only. And the name of that processor was Intel 4004. So it had like 2300 transistors. And the best part about these transistors were, that they were individually designed by some engineers, and even their locations in that entire chip was kind of selected, or it was strategically planned by the engineers themselves. So this kind of design where, the engineers plan and, they also determine the sizes or the functionalities of individual transistors, then it is called a full custom design, where, each and everything like the design of individual gates, the sizes of individual transistors, even their placement along the chip, entire thing is decided by the engineers. So this is kind of full custom design. Its kind of frequency of operation was 108 kilohertz, or the clock frequency was kind of 108 kilohertz. And this was built in 10 micron technology. So what does this 10 micron technology mean? So 10 micron technology, since it's a long channel device, so it simply means that, the gate length was 10 nanometers, or the difference or the distance between, or the half pitch length between two interconnect wires was 10 microns. However, such a definition for technology is not true once you go below, 14 nanometer technology or something. Also, in the late 1970s, people found out that, when you use PMOSFETs along with NMOSFETs, that is, when you use complementary logic, which is also called CMOS logic, then you can even, achieve performance gains which are better than NMOSFET only logic. And this CMOS technology has been, the driving force behind this semiconductor revolution, after 1980s. So till 1980s, I would say that BJTs were kind of dominating the market. After 1980s, it was CMOS static logic based circuit designs, which were kind of, dominating the market and leading the semiconductor industries. BJTs are used even now, but where are they used? So BJTs are used only where we require high gain or high speed of operation or high current drivability. Where do we need that? Wherever we have to transmit signals. For instance, in your mobile phones, close to the antenna, you have to have you need to transfer a large amount of power to the antenna because you need to transfer the signals to a large distance. So for that, BJTs are used. And that too not silicon BJTs, but another flavor of BJT, which is called heterojunction bipolar junction transistors, HBTs, they are kind of being used. So HBTs basically, instead of silicon, they use a different emitter. They use they can use SiGe, or they can also use like gallium arsenide based HBTs. So there are several flavors of HBTs as well. So yeah, typically it's not BJTs which are used, it's HBTs which are used even in that high speed requirement, wherever there is high speed requirement. And as I told, this CMOS kind of continues to dominate the market. Now, as the consumers are being aware, or I would say, as the consumer electronics is kind of improving, as a consumer, what we want is that our mobile phones or our consumer electronics should perform a lot of applications at the same time. So it should be multifunctional. I mean, a lot of functionality should be embedded in our devices. So for that, what we need is a large number of devices which implement these gates or these basic entities to be present on our chip. And for that, we need to reduce their size so as to accommodate more number of devices for the same area of the chip. So for that, we need to reduce the sizes of these transistors, and that process is known as scaling. So what exactly do we do in scaling? We reduce all the critical parameters of the transistors by a particular ratio, and that ratio is 0.7. So we'll discuss later why exactly 0.7 and how exactly it is able to follow that 0.7 kind of thing till 2010 or 12. So when you're reducing the length and the width of the transistor, which are two critical parameters, then you are typically reducing the area of the transistor. So once you are reducing the area, definitely you can pack more devices in the same area. So you can have large number of transistors per chip, per die, per wafer. Also, once you have large number of transistors per die, you can realize large number of logic functions or logic gates with those transistors, and as such, you can realize large number of functionality with that kind of when you scale down the devices. So there's something which is called as Moore's law. So this was kind of given by Gordon Moore, who was one of the co-founders of Intel. So there's an interesting story even behind Gordon Moore. So Gordon Moore was one of the employers, or I would say, Shockley, after discovery of transistor, he kind of found a startup, and then he employed Gordon Moore also there. So, but since he was an arrogant man, he was not a good manager. So he wasn't able to retain these people, and 8 of his employees, they kind of fled from there. And those 8 employees, they are themselves like leaders in the field of semiconductor industry right now. They include Gordon Moore. Like 3 major semiconductor industries in the Silicon Valley were found by those 8 people. So Gordon Moore was one of them. Robert Noyce had a very important role to play. He kind of poached them and he supported them to form this NM Electronics company, which later came to be known as Intel. He also continued to become the vice president and then CEO and then director of this Intel for some time. So Gordon Moore, what he did in 1960s, he kind of found out that every 18 months the amount of chips are kind of amount of transistors per chip is kind of doubling. So he kind of predicted that this trend, or that the number of transistors per chip will kind of double every 18 months. So if you look at this graph, it simply shows you the number of, I would say, transistors in microprocessors. So there are different microprocessors here. So it simply shows you that the number of chips in number of transistors per microprocessor, it kind of follows a linear relationship with time. However, this linear relationship is with the transistor count is plotted here in the log scale. So if something is linear, when the y-axis is plotted in log scale, then it's kind of having exponential dependence with the x-axis. So it's simply like this linear relationship with respect to a log scale y simply means that the number of transistor per chip or per processor, transistor count per processor is kind of increasing exponentially with time. So you can see that this linear relationship was maintained till I would say 2010 or something, but then it kind of, the slope has degraded and it has now kind of saturated. So there were few, nuances that were introduced beyond 2010 that led to kind of, saturation of the Moore's law, and that also we shall discuss. So apart from that, I mean, is that the only advantage? I mean, increasing of functionality, like packing more number of devices per chip, is that the only function? Like, is that the only advantage of this scaling? No. So this capacitance of the devices, each transistor comes up with a capacitance. So that capacitance depends upon area of the transistor. So if you're reducing the length and width together, you're also kind of reducing the area. And in most of these digital circuits or logic gates, you're kind of charging and discharging those device capacitances. Now, if your capacitance value is reducing, so if you're charging or discharging them with the same amount of current, then it will charge or discharge faster. So even the speed increases once you are reducing, your transistor device. Once you are reducing the device capacitance, even your speed increases. Also, your switching energy dissipation, it kind of reduces. So what exactly is switching energy dissipation? So when you go from logic 0 to logic 1, you are kind of changing the voltage across that capacitor from 0 to VDD. Similarly, when you are going from logic level high to logic level low, you are kind of discharging the capacitor's voltage from VDD to 0. Since you are playing with the voltage across the capacitor, the kind of relationship or the kind of energy that it draws from the supply during this charging or discharging from logic 0 to logic 1 or logic 1 to logic 0 is given by CV square. So I'll discuss that later in the next in the next few lectures. I'll discuss how exactly it's CV square. For the time being, you just take it as a word of mouth that the switching energy, that is the energy which is consumed by this capacitor while changing its logic from 0 to 1 or 1 to 0, that is proportional to CV square. And since it is proportional to CV square, by scaling your C is reducing, and therefore your switching energy also reduces. So this curve simply shows you the switching energy as a function of your gate length of the transistor. So as compared to 1 micron length of transistor, which is 1000 nanometer, you see that as we go or as we reduce the channel length to 100 nanometers, we see that the switching energy kind of decreases linearly when it is plotted on a log scale, or simply say the switching energy kind of reduces exponentially as you reduce the gate length. Since scaling improves your number of functionalities, or it reduces the device capacitances, it improves the speed, it also reduces the switching energy. It looks very promising that you continue reducing the dimensions of the transistors and your performance of CPUs will continue to increase, but that is not the case. Why so? Because the moment you enter into what is known as short channel regime, there are a lot of problems that arise in a MOSFET. So what exactly is a short channel MOSFET? So when the gate length of a MOSFET becomes comparable to the source channel or channel drain depletion region width of a MOSFET, then that MOSFET is called a short channel MOSFET. Now, why there exists a depletion region there? So typical MOSFETs, let's talk about N MOSFET. So it has got N plus source, P channel, and N plus drain. So because of this, like metallurgical junction, you would definitely have N plus P junction at the source channel interface and PN plus junction at the channel drain interface. So you'll have two depletion region widths. If the depletion region width is comparable to the channel length or the gate length of the transistor, then it is called a short channel device. So what is the typical boundary between long channel and short channel devices? So when you calculate the depletion region width, taking into account, let's say 10 per 20 doped, like N plus doped to 10 per 20 and P doped to 10 per 16, the order, or I would say the calculations would give you a depletion region width close to 350 nanometers. So you can assume that any channel length below 350 nanometers corresponds to a short channel device. Now, what exactly happens when the channel length reduces below 350 nanometer is several other artifacts come into picture. So what happens is most of the channel charge, though they should have been controlled by the gate, but now they are like they start to be controlled by your source channel or channel drain depletion region. So even drain region has some amount of control over this channel charge. Also, as you reduce your gate length, what happens is the drain electric fields, they kind of encroach towards your source channel like interface, and then increasing the drain voltage kind of reduces the barrier height between source and channel. That is also known as a DIBL, or drain induced barrier lowering effect. So to summarize, impact of all these short channel effects is an increase in the leakage current. So what exactly is the leakage current? So leakage current is the current that flows through a MOSFET when you apply a zero gate to source voltage. So you have a gate drain to source voltage, which is VDD, or the supply voltage, and you apply a zero voltage on the gate to source to turn off this device, but still you get some leakage current. Because it's a non-ideal switch, you still get some leakage current, and that leakage current becomes high because of these short channel effects. So as you reduce your gate lengths, your short channel effect increases, and because of that the leakage current increases. That is, even when your gate is off, it is draining some amount of power. So that is also known as static power dissipation. Why static? Because ideally on your device, some of them, like ideally on your chip, some of the transistors would be on, some will be off. So you don't want any power to be dissipated from the transistor which are off, which have VGS equals to 0. But still, because of this leakage current, because of this large leakage current, there would be a current which would be flowing in those transistors, and it would be draining up power equals to that supply voltage times the I leakage, right? So because of that, the static power dissipation increases, and you can see over here, which simply shows the CPU power density. So the CPU power density, they have kind of broken it up, or they have kind of decoupled the dynamic power dissipation shown over here, and the static power dissipation or the leakage power dissipation shown with blue. So as your gate length reduces from 1 microns to 100 nanometers, you can see that both static leakage or static power dissipation as well as the dynamic power dissipation, but this is density, it's power density. So both static power density as well as dynamic power density, they increase. However, there comes a gate length for which the static power dissipation kind of surpasses the dynamic power dissipation, and we have already reached those gate lengths. So it's close to 25 to 30 nanometers. So when you reduce the channel length below that, your static power dissipation becomes a dominant component, and your dynamic power dissipation is kind of less as compared to that. Earlier, the dynamic power dissipation used to be the dominant component of CPU power density, but nowadays it's static power density, which is kind of more dominant factor as compared to this dynamic power density. So for reducing dynamic power dissipation or the switching energy, we were reducing the capacitance, we were scaling the devices. However, from that area-centric, or I would say that area-centric perspective, now the design of digital circuits have moved towards a domain which is called power-centric design, or where reducing the leakage power is one of the major concerns. Now industries, they have come up with various novel approaches in order to sustain this Moore's law. They tried their level best to do so. However, nowadays it's saturated. Beyond 2010, Moore's law is saturated. So what happened? How the MOSFETs have evolved? They have evolved in architecture as well. So here you see a planar FET. Why it is called a planar FET? Because the source, channel, drain, they are all in one plane. There's no 3D protrusion of even channel or source or drain. So this is planar FET, which was the technology above, I would say, 14 nanometers. Below 14 nanometers, they had to introduce this fin, or I would say a projection of this channel. And this projection of the channel is then covered by the gate. So they had to protrude this channel, a thin cuboidal like protrusion on top, so that the gate could cover. So here, if you look at the planar FETs, the gate is just on top of this channel. So it's just covering, I would say, one side of the channel, right? The gate is on top of only one side of channel. So the gate is controlling the channel from only one side. Now, if you like protrude this channel like a fin, and then if you run a gate through it, then this gate kind of covers the channel from 1, 2, and 3. So it covers the channel from 3 sides. So in this fin-shaped channel FETs, which were also called as fin FETs, you have like the gate control from 3 sides. So if you reduce the channel area, which is being controlled by the gate, and if you have gates from more sides, you kind of effectively increase the impact of gate. or you make these devices electrostatically more integrated. I would say the gate electric field can modulate the channel characteristics more efficiently when you have gate control from more sides and when you have thin channel, because if you have thin channels, the electric field can penetrate the channel efficiently and it can modulate the electrostatics of the channel very efficiently. So from 14 nanometers till 5 nanometers, people went ahead with this FinFETs. Again, these 14 nanometers or 5 nanometers, let me make it very clear that this has nothing to do with the transistor dimensions, the gate lengths, or the half pitch length of two metal interconnects. This is just a name. Since by Moore's law, the technology nodes were shrinking by 0.7 times every 18 months. For instance, if the technology is 14 nanometers now, after 18 months, it will be multiplied by 0.7 and it has to become 10 nanometers, close to 10 nanometers, I would say. And then if it is 10 nanometers now, after 18 months, it will go from 10 nanometers to 10 into 0.7, that is 7 nanometers. So these are just names. These have nothing to do with the dimensions or feature sizes of the devices. So beyond 5 nanometers, people found out that even FinFETs were showing a large leakage current, and we had to improve the gate control further. So to further improve the gate control, they made these gate-all-around nanowires. So you see these silicon wires. So these wires are kind of being covered by the gates from all sides, from all four sides. So for less than 3 nanometer technology nodes, people have actually proposed these gate-all-around nanowire FETs. And recently, people came up with this multi-bridge channel FET. Samsung calls it as multi-bridge channel FET. Like IBM calls it nanosheet FETs. Like Intel also came up with it, and Intel is calling it a nano ribbon FET. But the structure is same. So instead of having a wire, what they're doing is they're having a sheet kind of structure, and this sheet has this gate covering it from all four sides. So this is the immediate replacement of FinFETs. So for 5 nanometers and beyond, people are actually going ahead with nanosheet transistors. So the main aim behind this evolution is to kind of reduce the leakage current. How can we reduce the leakage current? So as I told that these short channel effects manifest themselves by taking they kind of manifest themselves by taking a large amount of or controlling a large amount of channel charge. But here, if we have gates from all sides, then it kind of provides a better gate control, and loss of that channel charge to the source and drain depletion region is low. So all sorts of tricks are being played now, strain engineering and all sorts of things are being done in order to improve the electrostatic integrity, and in order to scale the transistors or architectures using or to sustain the Moore's law. But however, despite of all such efforts, we haven't been able to sustain it. So as I told, planar gate is on one side, FinFET gates are on 3 sides, so you have a better control of the channel region. And in gate-all-around and MBC, you have gate trapped all around the channel, and as such, it gives you the best possible gate control. So now we told that the Moore's law is saturating, but the device density or the scaling should be governed by some law, right? So here comes the Kumi's law, which is kind of more relevant to the present scenario. So what Kumi observed was that with every 18 months, the number of computations that is performed by the processor per kilowatt of power consumed when it is running it at its peak frequency. So what Kumi said was that he kind of plotted it, and he observed that even that follows same law as the Moore's law. That is every 18 months, the number of computations or the number of operations that are performed on the processor per kilowatt hour of power that it consumes when it is running at its peak frequency, that is also doubling every 18 months. And this has not saturated. So this is not saturated, this is continuing so. Why so? Because it is driven by more fundamental unit, which is power. So area is not that fundamental unit, power is a fundamental unit. And as such, we always, the industries always wanted to sustain the Moore's law. So they always wanted to go ahead, long live the Moore's law, but Moore's law is dead now. It's unfortunate that we haven't been able to innovate devices that could keep Moore's law alive, but Kumi's law is something that is still alive, and it is expected to be alive even further. So in this energy-driven world where everything is governed by energy, so we have IoT devices, we work with mobile devices, we work with smartwatches, we work with devices which are deployed in the remote areas which have less energy or where the energy constraint is there. So in all those devices, this Kumi's law is actually more fundamental, and it's kind of it will be sustained because its basis is more fundamental, that is an energy. And if you look at the power density of the present microprocessors, so the power density has increased significantly. So the temperatures on your the power density of your modern processors is close to the power density which is observed in the nuclear reactors. So it generates such a high amount of heat that you need to these servers, they require coolants and all. So in all these high performance computing systems or these servers, you need coolants or fans. CPU fans are there just to remove this heat. So the power density has reached to such an alarming levels in the circuits that we have to seriously think about reducing the static power dissipation